Hello students, good morning.
Good morning, ma'am.
Good morning my
Good
dear
morning,
students.
ma'am.
Good morning Sartika, Chaturya and all other friends. Alright, today uh, we will discuss about a stable mode of operation of the Wi-Fi timer. Okay, yesterday we have discussed thoroughly about monostable and a functional diagram of triple five timer, all that. So therefore, today I am directly going moving forward. Before that means every time I just go back and recollect. And today all that is not necessary. Now let me discuss about this stable mode of operation of triple five timer first, and after that we shall see after understanding this we shall see what is the frequency of oscillations, all that we will calculate. That means output frequency of okay. And after that I want to see what is that, I want to make you to do some problems. Only one problem I give and one problem as homework I want to give. If you are able to do, you can do, otherwise we will solve that problem in the class itself. And then we want to see applications. So that is the primary aim. And if time permits, we will also discuss about Smith trigger and a question bank from triple five timer. What are the questions got from triple five timer? So all these I am planning to discuss. Someone is making noise. You please check your device. Otherwise, I have to mute you. Okay, you please check your devices. Now, a stable mode of operation. The triple five timer functional diagram we know, right? And if we observe this triple five timer functional diagram, it has some analog and digital circuits, all that we have studied. And if you want to connect triple five timer monostable mode, we have connected one R and C, whereas in stable mode, this R is split into two parts, RA and RB. Only that is the difference from monostable mode to stable mode, right? So that means actual triple five timer, and its functional diagram we have seen. When we want to connect this triple five timer in monostable mode, what are the additional components that we connect? From VCC to ground, we connect one resistor and one capacitor in monostable mode. So in a stable mode also same thing. From VCC to ground, we connect resistor and capacitor. Only difference from monostable to stable is in monostable we have only one resistor, and in a stable mode of operation we split this resistor into two resistors, RA and RB. Both are same. Okay, so only that is the difference. I think you know why I am repeating these pin connections again and again means in the examination you should not feel difficult. Okay, so I think whenever I am showing this slide, you people are drawing this circuit diagram. So have you taken this diagram already yesterday, or you are taking now? You respond. You have taken this diagram yesterday, or you are taking now?
Yesterday over, ma'am.
Good. Thank you, Bindusri. Right. So between pin number 1 and 5, 0.01 microfarads capacitor. Third pin is the output pin, and we know 8th and 4th pins connected to VCC. And in a stable operation, one more modification is actually in monostable. For second pin, we give external trigger pulse. Here in a stable operation, it is also called as a free running oscillator. We do not give any external voltage across the capacitor only, right? Within the circuit we are connecting one capacitor now, so the voltage across the capacitor only is the voltage that is applied, trigger input that is applied to second pin. Okay? And sixth pin, all other connections are as usual, right? And seventh pin, discharge pin, is also connected at the center of these two resistors, at the junction of the resistors. These are the small changes that are from monostable to stable operation. Okay. Now let us see this detailed functional diagram, right? we know that within these dotted lines, what all we have is within these dotted lines, what all we draw is a 555 timer internal diagram, or 555 timer functional diagram, or 555 timer block diagram. Today I have gone through your previous question paper, right? Explain about the what is that block diagram of 555 timer they asked. So it is same, right? Block diagram or functional diagram, or what is that? Any diagram. Okay, so internal diagram, all these are same. Now, the internal diagram is same, so therefore, lower comparator, upper comparator, flip-flop, all these are same voltage divider circuit. So only thing is external to the internal diagram, RA, RB, and C capacitor. So these are the three additional components that we have to draw. I think you have taken this diagram yesterday, right? Am I correct? Have you taken this diagram yesterday?
No, ma'am.
Then all of you please draw this diagram, right? Because in the examinations they are asking draw the functional diagram of Astable Multivibrator using 555 timer and explain about each block. Then you have to explain, right? So the functional diagram you know how to draw. Just in front of that, from VCC to ground, you have to draw RA, RB, and C, right? So all of you please draw this functional diagram when I am explaining this. Okay. So we know about this clearly, lower comparator and upper comparator. So output of lower comparator and upper comparator controls this control flip-flop. So depending on that, if S equal to 1, Q will be 1, so output will be 1. If R is equal to 1, Q will be 0, output will be 0, right? So when this S is 1, otherwise when do we get lower comparator 1? When do we get upper comparator 1? Output 1. So that is the condition we want to know. So we know that for lower comparator, 1/3 VCC is given as reference voltage. And if you observe other input is the voltage across the capacitor only. Voltage across the capacitor only, right? So till now in monostable we have given external trigger pulse. But now in this stable mode, we are giving at second input voltage across the capacitor as the input voltage to the lower comparator, and a reference voltage is 1/3 VCC. Now here if we explain, if we understand, whenever the voltage across the capacitor passes this 1/3 VCC, then we will get lower comparator output 1, right? So that is what we want to say. Then you just observe the upper comparator, right? Upper comparator reference voltage is just 2/3 VCC. 2/3 VCC. You see, this capacitor is 0.01 microfarads capacitor, which is recommended by what is that manufacturers. Okay, so if at all, if you are not giving any external voltage to fifth pin, you connect it to 0.01 microfarads. Okay, so whatever it may be. Now at this pin we will have 2/3 VCC because of this 5 kilo ohm resistor. So 2/3 VCC is the reference voltage. Now what is the other input that is applied to compare the output of the to compare these two inputs? That is, other input is just you observe it is also voltage across the capacitor, right? So now voltage across the capacitor will be changing according to VCC. That means when you switch on the supply, the capacitor starts charging. Why? When you switch on this VCC, through this RA and RB, capacitor will be charging, right? So how it is charging? Depending on the values of resistor R and C, it will be slowly charging. Okay. So when a capacitor voltage reaches some voltage here, the lower comparator will give its output, and when the capacitor voltage slowly it is charging. When it reaches to another voltage, that is 2/3 VCC, upper comparator will give its output as 1. Okay, so that means voltage across the capacitor only is the threshold voltage and also the trigger voltage. threshold voltage, threshold pin. Pin number 6 is threshold pin. Pin number 2 is trigger pin. Okay. So both the pins we give voltage across the capacitor only. So now you know if I mention what is the reference voltage, that is sufficient, and this remaining part you know. That means when upper comparator output is 1, flip-flop is reset to 0. So when Q is 0, and here you can see Q bar is 1. When Q bar is 1, this transistor will be in on condition. When this, you just observe one more change here. So the discharge pin or this transistor is connected to this junction of resistors RA and RB, externally connected resistors RA and RB. So when this is 1, this transistor will be like closed switch. Therefore, that means you just observe this is closed path, and between ground and this point there is capacitor. That means when it is like closed switch, this capacitor will be discharging through this path. Okay, capacitor will be discharging through this path. When it is like open switch, the capacitor will be charging from VCC. If you observe during charging process, resistor RA and RB are included, and during discharge process, only resistor RB is included, connected. Okay, so that is the circuit arrangement. So now, when it starts discharging, what happens? The voltage across the capacitor will be reducing, coming to 0, right? Now, by the time it comes to 1/3 VCC, what will happen? The input to the lower comparator, it is crossing. Therefore, again it will be the when the voltage across this voltage across this capacitor reaches slightly less than 1/3 VCC. That means when it crosses 1/3 VCC, then this lower comparator will set its output 1, right? So therefore, it is in its discharge path when it travels up to 1/3 VCC. Now lower comparator output is 1. Therefore, flip-flop S is set to 1. So Q will be 1. Then Q bar will be 0. When Q bar is 0, this transistor is like an open circuit, right? So this transistor is like open switch. Now when it is open switch, now there is no clamp here, no short circuit here. When it is open switch, now the capacitor starts charging to VCC. So therefore, whenever that is happening, now capacitor again starts charging, right? So again, when the capacitor voltage reaches slightly 2/3 VCC, when it crosses 2/3 VCC, again upper comparator will set its output as 1. So control flip-flop will be set to 0. That means reset to 0. When output is 0, Q is 0, Q bar is 1. So when Q bar is 1, transistor will be on, and now the capacitor will be discharging. That means capacitor is charging from what is that? Some charging initially up to 2/3 VCC, and again it is discharging. When it comes up to 1/3 VCC, again capacitor starts charging, discharging. That means, so the charge and discharge of the capacitor is controlling, is making the voltages available at lower comparator and upper comparator different values. Accordingly, the upper comparator and lower comparator gives their outputs, and finally the control flip-flop will be giving either output 0 or 1. So finally what will happen? So during charging process, output is 1, and during discharge process output will be 0, again 1, again 0. If you observe, it is a free running oscillator. We are not giving any external voltage, just we are switching on this VCC supply, right? So this is what about the functional diagram of astable multivibrator using 555 timer. Is it clear? Here it is. Instead of saying a lower comparator, inverting comparator, upper comparator, non-inverting comparator, output is plus Vsat, minus Vsat, all those we know. So directly what we are saying is when the voltage across the capacitor, okay, so otherwise input at inverting input terminal crosses the reference voltage, output will be 1 here also, right? So when voltage at non-inverting input terminal crosses 2/3 VCC, output will be 1. Both are same. So to make your life simple, I am just explaining like that. Okay. We know perfectly about comparators. When reference voltage, when input voltage is greater than reference voltage, output will be plus Vsat, and if it is less, output will be minus Vsat for non-inverting comparator, and for inverting comparator, it is reverse. Okay. So all that we know, we have learned about the comparator very clearly. So I hope this circuit is quite clear to you, and the explanation what I have given is quite clear to you. Now, if I show you the waveforms, right, you just observe our capacitor voltage is charging, right? So up to 2/3 VCC it is charging, right? Then it is discharging during discharge process, right? Now, when it reaches to 1/3 VCC, again the charging process starts. So that means if you observe the voltage across the capacitor, it is varying from 1/3 VCC to 2/3 VCC, 1/3 VCC to 2/3 VCC. And during this charging process, we know Q is at 1, therefore output will be 1. And during discharge process, we know Q is at a reset stage, therefore Q is 0. So like that, charge and discharge, otherwise output is, this is the output waveform. So output will be 1 and 0, 1 and 0, like that. So this period is called total time period. Both charge and discharge period is called total time period. And this is T high, that means where the output is high, and this is T low, where the output is low. Okay. So that is about the output waveform, and this is the voltage across the capacitor. I think both are very clear to you, right? Am I correct? Is it clear to you?
Yes,
Is
ma'am.
this? Yes, very good, very good. Okay, then let us move little forward, and let us express the same thing in mathematical form or in equation form. Okay, so we know that the capacitor voltage for this low pass RC circuit, when we apply a input of VCC, then capacitor voltage VC, we are just naming capacitor voltage VC is equal to VCC into 1 minus e power minus t by RC. VC is equal to VCC into 1 minus e power minus t by RC. This is the voltage across the capacitor for your input voltage of step input voltage of VCC when we apply it. Okay. So when you apply this VCC, voltage across the capacitor VC can be expressed like this. Okay. Now let us add some more terms here, right? So let us say the time t1 taken by the capacitor to charge from not the capacitor exactly, circuit, let us say. So time t1 is taken to charge the capacitor from 0 to 2/3 VCC. So when the voltage across the capacitor is equal to 2/3 VCC, then what is the time? We are mentioning it as t1. So VC is 2/3 VCC when t is equal to t1. So therefore 2/3 VCC is equal to VCC into 1 minus e power minus t1 by RC. Same way we have calculated a time period for monostable multi also. Here also we will calculate in the same manner. Okay. So 2/3 VCC. Now internal calculations also I have done for monostable. So because I have shown you the way, I am not doing all the internal calculations. So VCC gets cancelled. 2/3 minus 1 is equal to minus e power minus t1 by RC. Then t1 will be, you just calculate and tell me, t1 will be 1.09 RC or 1.1 RC, whatever you get. Okay, you please calculate and tell me. Same way what we got for earlier, we have made it as 1.1 RC. Now you please take like this only, right? T1 is equal to, let us take 2 digits, that's what I want to say. So T1 is equal to 1.09 RC. Okay, after rearranging this and calculating for T1, we will get this one, right? So if you have done that, you please share that in the chat box. Let me see. Let me see. Okay. Then let us take what is the time T2. Let us define the time T2. Okay. So time T2 is to charge from 0 to 1/3 VCC because it has to change from 0 to 1/3 VCC and then it has to charge from 1/3 VCC to 2/3 VCC. Okay. So therefore, let us take this time as T2 to charge from 0 to 1/3 VCC. Now in the same equation, so 1/3 VCC is equal to, okay, 1/3 VCC is equal to, now it should be T2. So it is T2 only. It is not that much clear. So you just take it as T2, T2, right? So 1/3 VCC in equal to VCC into 1 minus e power minus T2 by RC. And again, when you rearrange, you will get T2 is equal to 0.405 times RC, right? So this is what we get. I think this type of calculation we have done for monostable, and similarly if we are doing now. So I think I can move forward without verifying your calculations. Am I correct? Shall I move forward? T2 is equal to 0.405 RC.
Yes, ma'am.
Yes, very good, very good. Right. Now, let us see what is the time to charge from 1/3 VCC to 2/3 VCC. Why we want a charge from 1/3 VCC to 2/3 VCC? This is 1/3 VCC. So, and from 1/3 VCC to 2/3 VCC is called only that time output is high. Therefore, let us take this time period. So that is T high. And from 2/3 VCC to 1/3 VCC, this part we call it as too low, T low. So therefore, let us take those two. Okay. So now the time taken, the time to charge from 1/3 VCC to 2/3 VCC is T high. Just now I have shown in the diagram. Okay, waveform. So T high is equal to what? T1 minus T2. That means what is the time taken? What is T1? T1 is the time taken to charge up to 2/3 VCC, and T1 is the time taken to charge up to 1/3 VCC. Now T2 minus T1 shows from 1/3 VCC to 2/3 VCC how much time it is taking. So T high is equal to T1 minus T2, right? So we got what is T1 and we got what is T2, and you will get what is T high, right? So it is 0.69 times RC. That means T high is equal to T1 minus T2. T1 is 1.09 times RC minus T2 is 0.405 times RC, and if you subtract, you will get 0.69 times RC. So T high is equal to 0.69 times RC. So therefore, we can write what is R? R is nothing but RA plus RB. We have split this R into two parts. Okay. So for convenience sake, we have written R, that's all. So T high is equal to, now T high is equal to 0.69 times 0.69 times RA plus RB into C, right? T high is equal to 0.69 times RA plus RB into C, right? So this is T high. Then what is T low, right? So the output is low when the output is low. Output is low when the capacitor is discharging from 2/3 VCC to 1/3 VCC, right? So you just observe, you know already, but for my satisfaction, I'm telling, right? So when the capacitor is discharging from 2/3 VCC to 1/3 VCC, output is low, right? So that is what we want to calculate, right? So output is low when the capacitor discharges from 2/3 VCC to 1/3 VCC. Now that means the voltage across the capacitor is now how much? It is 1/3 VCC because it is reaching up to 1/3 VCC, reaching down up to 1/3 VCC, right? So and its starting voltage is 2/3 VCC. Therefore, 1/3 VCC is equal to 2/3 VCC into e power t low e power minus t by RC. So this t is nothing but our t low, right? So we will get t is equal to what is that? 0.69 times RC we will get 0.69 times RC. So this t is nothing but t low. So t low is equal to 0.69 times RC. Now actually R is nothing but RA plus RB I said. But now in this equation I am substituting only RB. Anybody can mention? Anybody can answer why I have written only RB? T low during discharge process, the resistance in the circuit is RB only, right? So why I have written RB only in place of actually when we have R, we write RA plus RB during charging process. But discharge process in place of R, I am writing RB only. Anyone can answer why I have written only RB, why not RA? I'm giving you hint. You see the functional diagram. During discharge path, what are the resistors that are coming into picture? And during charging path, what are the resistors that are coming into picture? Right? Just see the functional diagram. Right? You just observe. During when is output high during charging process? So during charging process, capacitor charges through RA and RB. So therefore, wherever we have R, we have written RA plus RB. Is it clear? Now during discharge process, discharge means when this transistor is in on condition, you just observe this transistor is connected to this junction. So now this capacitor discharges through RB and this short circuit. Okay. So therefore, during discharge path, only resistor RB is coming into picture. That's why for T low, I have written RB. This R is replaced with RB, right? So during charging process, both RA and RB are coming into picture when the capacitor is charging. But when the capacitor is discharging, the resistor RB only is coming into picture because that is the resistor connected to transistor, right? So therefore, RB only I am writing. Is it clear to you or not? Is this clear to you?
Yes, ma'am.
Very good. Okay. So of course here it is mentioned already. So note that both RA and RB are in charge path, but only RB is there in discharge path. Okay. So now we know what is total T. T is equal to T high plus T low, and you add both, you will get total T, and F is equal to 1 by T. And if you just calculate 1 by 0.69 into RA plus 2RB into C, that means 1 by 0.69, you will get F is equal to 1.45 divided by 1.45 divided by RA plus 2RB into C. I think for us, we are very much habituated to write total time period. So if this is easy to remember, you remember this 1 by T you can write later, right? So T is equal to 0.69 RC. For monostable, it is 1.1 RC, and here it is 0.69 RC. That's all. So for monostable, we write R is single R. For astable, we will get RA plus 2RB, right? So when you calculate total T, you will get like this. Okay. So this is what about the frequency. That means free running frequency. That means the frequency output. The output of the Astable multivibrator is the output. It is like a square wave, and this is also called as a free running oscillator. Therefore, this frequency is also called as free running frequency. So what is this free running frequency for this Astable multivibrator is 1.45 divided by RA plus 2RB into C, right? So I'm telling you the simplest way. T equal to some constant into RC. If it is monostable, 1.1 into RC. for it, if it is stable, 0.69 into RA plus 2 RB into C, because this RB is coming 2 times. Okay, so during charge path, RB is coming. During discharge path, RB is coming. Therefore, we get 2 times. Okay, so this is what about the frequency of oscillations. That means oscillation frequency or output frequency of the stable multivibrator. This frequency is also called as free running frequency, right? Now, because it is the output, we can say we can also calculate the another term, that is duty cycle. Duty cycle. So, what is this duty cycle? I think whenever we talk about square wave or rectangular wave, we talk about duty cycle, right? I think this is one type of square wave, and this is another type of square wave. Of course, another type of square wave we can say with the duty cycle or rectangular wave, and perfectly like this is another type. So from waveform 1 to 2, 2 to 3, the duty cycle varies. Okay, we are familiar with this duty cycle. What is this duty cycle? Duty cycle is the ratio of on time to the total time period. For example, this is the total time period T. This is the total time period T. Then the on period is this much. On time is this much. So on time divided by total time period is the duty cycle. Is the duty cycle. Okay. Now, for our circuit, if you observe, when which one we take as on period means this is the on period. That means when the transistor is in on condition, what is happening? When the transistor is in on condition, it is like short circuit. So therefore, capacitor is discharging. Therefore, this is defined as on period. That means it is T low, right? So for our circuit, we are taking what is that percentage? Always it is expressed in terms of percentage. Therefore, D, duty cycle D, is expressed in percentage, is equal to T low divided by total time period. So when is this T low? T low equation we know. So what is T low? T low is equal to, here we have, right? T low is equal to 0.69 times RB into C, right? So what is total time period? T is equal to 0.69 into RA plus 2 RB into C, right? So T low divided by total T you can write, and then you will get T low divided by total T multiplied with 100. So R and C gets cancelled, and you will get RB by RA plus 2 RB, right? So this is what we will get. And now that means the duty cycle depends on the resistor selection, that is RA and RB, right? So that is what about the duty cycle of your stable multivibrator. And if you observe this equation, so RB by RA plus 2 RB. So if the duty cycle is 50%, what do you mean by 50%? On period 50%, off period 50%. That means T on is we say T on is T, and this is half of T by 2, right? T on period divided by half of T is on period, right? Divided by total time period. So total time period. So T gets cancelled. It will be 1 by 2. It is 0.5 or 50% duty cycle, right? So when this numerator is smaller and denominator is less, then you will get less than 50% duty cycle for this type of stable multi, because this is, for example, let us say RB is 1 kilo ohm, right? RA is 2 kilo ohms. Then RB by 2 kilo ohms plus again 2 kilo ohms. So some numerator, some higher value you will get. Therefore, it will be naturally less than 50% duty cycle we will get with this type of arrangement. Okay. So therefore, what we do is we can have another arrangement, that is an alternator circuit where during discharge path, are during charging path. During charging path, one diode is connected across this RB. Diode is connected across RB. Then what will happen? You just observe during charging process, only RA is coming into picture, right? So like that, now this equation can be modified, right? So T high also will be 0.69 times RA into C. Earlier we have 0.69 times RA plus RB into C we have written. Now during charging, because of the presence of this diode, when it will be in forward biased condition, so it is almost like short circuit. Therefore, this resistor is short circuited. Therefore, its presence will be 0, and therefore T high can be calculated with RA only, right? So like that, when we have only RA, then it is possible to have more than 50% duty cycle, right? It is adjustable duty cycle when you keep one potentiometer here, right? You know what is duty cycle, and it is depending on what factors. Okay, duty cycle is depending on RB and RA, right? So at resistor RA, if you place one potentiometer, right, you can have adjustable duty cycle, right? So same, what is that? Astable multi, same astable multi, and R is divided into RA, RB, but with RA, we add one more potentiometer for adjustment's sake, that's all. And RB is made, what is that? Made short circuited here, so that during charging path, its presence will not be there. During discharge path, its presence will be there. So actually, if you remove this RB during discharge path, what will happen? Let me tell you one word, then we'll move forward, right? So you just observe this, what is that? Internal functional diagram, right? The capacitor is charged through RA and RB, and during discharge process, if you do not have this resistor, or if you remove these resistors, the transistor will be damaged. That means from the capacitor is charged to a certain voltage. During discharge path, if we have some control over the current that is flowing, then that means this is the resistor limiting the current. Okay, if you make this RA and RB 0, then what will happen means the transistor will experience very high currents. So the transistor gets damaged. Once when the transistor gets damaged, which in turn the total timer gets damaged. Therefore, the presence of RA and RB are required, and therefore we have modified. We can have adjustable duty cycle, astable multi with this one diode arrangement. I hope you have followed about the astable multi, right? So this adjustable duty cycle arrangement, because it is only one word, I'm just telling you, right? Across the resistor, one diode you connect and one potentiometer for adjustment. This is not that much required in the examination point of view. For the knowledge, just giving you some additional information. Okay. Now we can see the applications of 555 timer in astable mode. Okay, applications of 555 timer in astable mode. Okay, it is used in two different applications, mainly two different applications. One is one as FSK generator, that means frequency shift keying generator. The second one is pulse position modulator, right? For these two applications, the 555 timer can be used very widely, and many other applications also there. And now, when the 555 timer is connected in astable mode, these are some main applications, right? Let me tell you how frequency shift keying, how it can be used as a FSK generator. That means frequency shift keying generator. So I think you are studying now itself, you are studying digital communications. You know what is this frequency shift key, right? So here binary code will be there. Binary code will be there. Binary means bit or binary digit, either 0 or 1. For 0, one frequency is assigned. For 1, another frequency is assigned, right? Now binary code is transmitted by shifting a carrier frequency between these two frequencies. Okay, so like that we have this type of transmission. That means shifting the carrier frequency between between any two preset frequencies is called frequency shift keying. Is called frequency shift keying. Okay, so how is it possible to have these two frequencies from the same circuit, right? We know that our Astable multi, it can generate, it is a free running oscillator, it can generate the frequency output square wave of required frequency. Now, the same circuit, how it is able to generate two different types of frequencies, because for your frequency shift keying, two frequencies are required. One is 1070. This is the standard that is used for FSK signals. Therefore, for certain application like teletypewriting. Okay, so 1070 is one frequency that is required to be generated from this 1070 hertz is required to be generated. Hertz square wave should be generated from the output of this Astable multivibrator. And from the same circuit, we also want to generate 1270 hertz, right? So that means 1270 hertz frequency also. So how is it possible to generate these two frequencies from this Astable multivibrator? We are going to see, right? So now you just observe, I think the complete circuit is the right side of this. This is completely an Astable multivibrator circuit. You know, resistor from VCC to ground, R and C are connected. R is split into two parts, RA and RB and C, all that we know. And second pin and also sixth pin both are connected to capacitor. Therefore, voltage across the capacitor is applied to sixth pin and also to second pin. And between pin number 5 and 1, what is that? According to the manufacturer's recommendations, we connect 0.01 microfarads capacitor. This is the output pin. 4th and 8th pins are connected to ground. So, except this, all this is our Astable multivibrator, what we have studied just now, right? In addition to that, if we add two components, one transistor, of course, with some internal resistance, one transistor and one more resistor RC, it is possible to generate two frequencies. So how is it possible to generate these frequencies means you just observe, right? When input is low, what happens? This will be like this transistor will be like forward bias transistor. Otherwise, you assume this transistor will act as a switch, right? So when it is forward biased, it will act as a closed switch. When it is reverse biased, it will act as an open switch. Now, when it is a closed switch, that means, okay, depending on the input. Okay, when it acts as a closed switch, you just observe when it is like a closed switch, you just observe it is connected to the circuit. Okay, so now that means discharge pin is connected here. So capacitor will be discharging through this. That means our actual circuit. Now, when it is like open switch, when it is like open switch, that means when transistor is like open switch, so it is like nothing connected here. So our circuit will work as ordinary Astable multi, right? So that means when the input is, now I will tell you clearly, right? So when the input is high, right? Input is a digital data with some magnitude and frequency, right? So when the input is high, what will happen? When the input is high, the transistor will be in off condition, right? So for high input, the transistor will be in off condition or in cutoff. Therefore, there is no connection. The impact of all these components are not there. So the Astable multivibrator will act as original Astable multivibrator and it will give certain frequency. To what frequency you have designed? That means you have designed this Astable multivibrator to generate, for example, let us say 1070 hertz. It will give that frequency. Otherwise, if you design it to give some frequency F1, to that frequency it will generate. it will generate frequency signal of that frequency, right? Now, when the input goes low, when the input is low, what happens? This transistor will be in on condition, right? So it will be like powered bias and it will be in on condition. Now, if you observe, if you observe, if it is in on condition, this is RC and this is RA, right? So RC and RA are like both parallel resistors. Okay, both are connected in parallel. So actually, what is the output frequency for our Astable multivibrator? It is equal to 1.45 by 1.45 by how much it is? Let me show you. Output frequency F is equal to, right? Output frequency F is equal to ordinary Astable multivibrator. It is 1.45 divided by RA plus 2 RB into C, right? Now, what is happening during when the signal goes low, RA is connected in parallel with RC, right? So you just observe. So therefore, this equation is modified into RC. I will show you that equation. So like that, when RA is coming, RC is coming in parallel with RA, now the resistance is reduced. When R is varied, output frequency varies. So like that, when the input is high, it will act as ordinary Astable multivibrator. When input is low, it will act as ordinary Astable multi only. But RC is coming shunting here, right? So resistance will be reduced. Because of that, there will be variation in the frequency. Therefore, what is the frequency F naught that we get here is, okay, initially when the input is high, transistor Q1 is off and the 555 timer works as a normal Astable mode of operation, then frequency F is equal to 1.45 divided by RA plus 2 RB into C, right? So though I have here, why I have taken you to the previous slide is just to connect to you, okay? Now this is one F naught. Now, if you want to, when the input goes low, then Q will be in on condition and RC and RA will be in parallel. RC comes in parallel with RA as I have shown in the figure. Therefore, you will get here I forgot to write C, right? That C also I have to write. And therefore, it is F is equal to 1.45 divided by RA in parallel with RC plus 2 times RB into C, right? 2 times RB into C. So like that, the frequency can be adjusted. That means if you adjust this resistance RC, you can get the output equal to 1270. Next frequency you can have. So like that, okay. Initially, when there is no presence of all this, it is like a ordinary Astable multivibrator, and we will get 1070 hertz because we have selected RA, RB, and RC in such a way to generate F equal to 1070. Right now, when this RC comes in parallel with this, then you can get modification in the frequency. And for this RA and RC both, we have made potentiometers so that you can adjust the output frequency to 1270 hertz. So like that, we can use this Astable multivibrator as FSK generator. So what is FSK generation? Frequency shift keying. So what is this frequency shift keying? Binary code. Binary code is transmitted by shifting between 2 carrier frequencies. One carrier frequency is, for example, for a teletypewriter, one carrier frequency is 1070 hertz, and for another carrier frequency is 1270 hertz. So that example I have shown, right? Now, the second application is pulse position modulator. And if you observe this second example, second application, no modifications, just what is that? Same connection, right? Third pin, output pin, and a second pin is connected to second pin, and second pin is connected to sixth pin and RC. That means just IC as it is, only thing external RA, RB, C same. So no change at all in pulse position modulator. That means what we do is here at the modulating input signal, we apply a modulating signal. That means at control voltage. What is this pin, ma? Control pin, right? So control voltage we have to give here. So if you give some modulating signal, either a sine wave or a triangular wave, whatever you want, if you give, you will get the output as pulse. Actually, square wave it should give. Now reference voltage is changing now. Therefore, accordingly, we will get a different pulse width with the different positions. Okay. So like that, we can design a pulse position modulator using this 555 timer just by connecting some modulating signal to pin number 5. I think it is clear to you, right? Is it clear to you, ma'am? Like our pulse width modulation for monostable multi, here also we are giving modulating signal at the 5th pin and we can get pulse position modulated signal. So you just observe in this one modulating signal, which is a what is that? A small a triangular wave, right? A triangular wave is connected here, right? This is the modulating signal, and for this modulating signal, what is the corresponding output is shown, right? So for this triangular wave modulation, for this triangular wave modulating signal, and this is the corresponding output. So like that, the 555 timer can be connected, can be used for generating effect and pulse position modulated signal, right? So actually I plan to give you one problem also. All of you please take this problem. Otherwise, okay, we'll do this problem. Okay, better to do now itself. Okay, then we can, because we have only less time, we'll do this problem. In the next class, we shall discuss about Smith trigger and the what is that? The question bank from this part of unit 4. Okay. Otherwise, if you want to do this problem later, we can complete this Smith trigger also. Smith trigger also very simple concept. Okay. Okay. Anyhow, it is given as a essay question for you in the examination. So let me not be over ambitious. So let all of you please note down this problem and let us try to calculate these values. In the next class, we shall discuss about the Smith trigger and the questions that we got from 555 timer only, right? This is one part of our fourth unit, upper part of our fourth unit. And with the Smith trigger, we'll complete this. And later, we will study about PLL. Okay. All of you, please note down this problem. For the Astable Multivibrator circuit shown in this figure, then RA is equal to 6.8 kilo ohms and RB is equal to 3.3 kilo ohms and C is equal to 0.1 microfarads. Calculate what is T high, right? High time period, this one, right? And what is T low? Then what is the free running frequency F? And calculate what is duty cycle, right? So all the concepts that we have learned just now, we are going to apply so that you will have a more clarity. When we do problems, we will have more clarity, right? Even last year question paper, one more problem is there, one design problem is there, right? The next class, right? Because we are coming to the end of the class. You please do this problem. Meanwhile, let me take your attendance. There are 48 attendees only today. Okay. Please calculate what is T high. Okay, very good, ma. In between, when I asked this, some of you, Geeta shared. Oh, not only Geeta, very good. Nirmal Roy, Geeta. Very good, ma. They are very sharp. Right now, all of you, calculate what is T high and share your answer in the chat box. Right? T high. T high is equal to, we have derived the expression T high is equal to, even if you do not remember the derivation, you know what is T high. T is equal to something into RC, 0.69 into RC, and R is here RA RB. Therefore, T high is equal to 0.69 into RA plus RB into C. RA, RB and C values are given to you. You calculate and tell me what is T high. What is T high? I hope some of you are calculating. T high is equal to 0.69 into, I think I need not utter all these values. I have given you these values already. Please calculate what is T high and tell. Of course, kilo ohms and microfarads values are there. Carefully you calculate T high. How much? Okay. T high is equal to, it is 0.6969 milliseconds is correct. Approximately it is 0.7 milliseconds. Okay, Nirmal Roy. You cannot take 1.09, no? You have to take T high is equal to how much, ma? T high is equal to 0.69 into RA plus RB into C. Right? So, that is T2, kada? That is T2. So, T high we have done separately. Geeta, you just observe. Right? T high is equal to, okay, you observe separately. I'll show you this better. Okay, I'm just showing what is T high. T is equal to T high plus T low, right? What is T high? T high is this, right? What are T1 and T2? T2 is the time taken to go for to charge up to 2/3 VCC, right? And T1 is from 1/3 to from 0 to 1/3 VCC. T high is T1 minus T2, right? So when you substitute all that, T high you will get it as 0.69 RC. It is 0.69 into RA plus RB into C, right? So Geeta, you please verify once. And okay, you share the answer for the problem, for the given problem, that is 0.7 milliseconds. Then what is T low, ma? What is T low? Have you shared? T high is okay, right? I think Geeta, you might have followed what is T1, T2 and what is T high, T low, right? Now, calculate all of you. T low is equal to, we have T low is equal to 0.69 RC. 0.69 R is RB, right? RB is 3.3 kilo ohms and C microfarads. All of you calculate what is T low. T low. Right? After completing this problem, we will stop. Okay, don't be in a hurry to close the class. Right? T low is equal to how much? 0.227. Okay, 0.23 milliseconds we got here. Okay, you are correct. All of you give 3 or 4 digits after decimal point. Okay, Geeta, very good. 0.2277 milliseconds. Nirmal Roy, very good. 0.2277 milliseconds. 0.2277 milliseconds. Those who completed this, you calculate F. What is frequency F? F is equal to, F is, yes, Bindusri, correct, 0.2277. Is there any difficulty in calculating T high? All of you, I think you can calculate T high also. T high and T low. Then calculate F value. F is equal to, we have the expression F is equal to, it is 1 by T, 1 by total time period T. F is equal to 1.45 divided by RA plus 2RB into C. So you just substitute all these values and calculate what is F. You see, for these values, what is the value of F you get? You will wonder to see the value of F. Of course, any value it can be. Just those who have calculated, only 3 or 4 people are sharing their answers here, right? All others also, you have to share. Yes, very good. 1.08, you got 1.082 kilohertz, right? F equal to, of course, here we got 1.07, right? All of you give 3 digits, 1.08 or 1.07 kilohertz you will get. After that, you please calculate the duty cycle D. D is equal to T low by T, total T. It is equal to RB by RA plus 2RB. You calculate what is the duty cycle D. How much percentage you are getting duty cycle, you calculate. Okay, I think we have come to the end of the class. Let me take your attendance once again. And at the same time, all of you share your responses here so that you will enjoy the subject and we also will have confidence that all are listening, right? So my recording I will stop. Yes, very good, very good. Indusri, Monica, Geeta. Okay, right. And Geeta, right. Nirmal Roy, all these. Okay, same names repeatedly I am observing, but in a class of 60 students, 58 students, right? If I get response only from 1 or 2 students or less than 10 members, I'm not satisfied. Okay, all of you should respond. All of you please calculate and share your responses. Okay, Nirmal Roy, correct it is 24.6 percentage, I think, right? Percent you have to write. Duty cycle is always expressed in terms of percentage. So you please write 24.62%. Very good, right. So very good, new name, Pragna, Sai Pragna. D Sai Pragna 420, 24.62%. Very good. Geeta and Chaturya, very good. Nirmal Roy, very good. Right. Then Sai Monica. All of you please calculate all these values. And now I have exceeded, I think, 2 or 3 minutes time. No problem. In our regular class, if we exceed 2 or 3 minutes, but you what do you gain? You gain good marks in the examination, right? So because we have learned all these concepts, immediately we are doing, right? Harshavardhan, I think, right? Harshavardhan. Okay, so many of you are getting correct values. Very good. So I stop my recording.